Hi everyone. So let's discuss about the most important protocol in the network layer, which is the internet protocol. Also we call it as IP. Okay. So as you are aware, network layer sits on top of the data link layer and it provides services to the transport layer. Now, along with IP or your internet protocol, there are other protocols also which work in the network layer, but IP is the primary protocol and the remaining ones do actually help IP to do its task properly. So the main protocol of the network layer or the internet protocol IP is responsible for packetizing, forwarding and delivery of a packet at the network layer. So along with IP, I can also show you that there is one ICMP here, another one is IGMP, another one is ARP and RARP. So what is the purpose of these four protocols? The entire routing, addressing is actually taken care of by the IP itself. But for IP to work properly, we call them as sister protocols: ICMP, IGMP, ARP and RARP. So ICMP actually stands for Internet Control Message Protocol version 4, ICMP v4, which helps IPv4 to handle some errors that may occur in the network layer delivery. In order to convey the information regarding any errors that might have happened, ICMP is used. Similarly, IGMP, which stands for Internet Group Management Protocol, it is used to create the multicast groups or for the multicasting or multicast delivery. All of those things are taken care of by your IGMP protocol. ARP or the Address Resolution Protocol is used to glue the network and the data link layers in mapping network layer addresses to link layer addresses. So if I know the IP address and if I want to find out the MAC address, then I use the ARP protocol. RARP actually stands for Reverse ARP, which does the reverse way of finding out. If I know the MAC address and if I want to find out the IP address, then I can use this. Now, there are two common versions of IP in use today. One of it is the IPv4 and the other one is the IPv6. Every day what you see is the 32-bit address of IPv4 that is most widely used. But it has some issues regarding the address space exhaustion. So now a new version of this protocol called as IPv6 is now proposed, which might ultimately replace IPv4. Even before we go to the IPv4 header, I want to just give some little bit of discussion about IP, what it actually does, and what are its main characteristics. From that point onwards, we can start discussing about the header, their the respective fields, and their functionalities. So IP is designed as a protocol with low overhead. In the network layer, I don't want to have a lot of burden and a very complex protocol. So IP is a simple protocol with a low overhead. It provides only the functions that are necessary to deliver a packet from a source to a destination over an interconnected system of networks. What it does is you design a protocol which is used for transmitting packets from one point to another point. Doesn't matter where it is situated. It might be in different networks, but still, if even though a source is in one network and a destination is situated in another network, this protocol has been designed in such a way that it helps the packets to traverse this network so that they will be reached by the, or they will be reached at the destination. The protocol was not designed to track and manage the flow of packets. In another sense, it does not provide you the error control. It does not provide you the flow control. It doesn't guarantee you the delivery. It doesn't do that. So if he starts doing all of those things, the low overhead does not suit anymore. IP encapsulates the transport layer segment or other data by adding an IP header. So whichever data is actually being sent by the transport layer, you know that network layer sits under the transport layer. So when the transport layer sends the data to the network layer, the IP accepts it. It adds an IP header to it. We call this as an encapsulation process or called as packetizing. And then you forward it to the bottom data link layer. The IP header is used to deliver the packet to the destination host. So based on this, let me give you some of the basic characteristics of IP protocol. The first characteristic is the connectionless nature of it. There are no connections that are established with IP. You simply take a packet, write the full destination address and inject it into the network. Let the network take the responsibility of delivering this packet to the destination. So there is no connection with the destination established before sending data packets. The second characteristic is best effort service. IP does not guarantee you the delivery of data to the destination. It will accept the packets, and based on the destination address, it will try to find a route to the destination if one exists. So IP is inherently unreliable because packet delivery is not guaranteed. So we call it as a best effort service. The third characteristic, most important one, is media independent. Doesn't matter if you are using a copper connection or an optical fiber connection or even wireless connection. Doesn't matter which media you are using to connect to the network. Irrespective of the media, independent of the media, your IP protocol will work in a common way. So operation is independent of the medium carrying the data. So your IP protocol does not change based on the medium through which you are connecting to the internet. So these are the three basic characteristics of IP protocol: connectionless service, best effort service, and it is media independent. With this, let's see how an IPv4 header looks like. So obviously, as I told you, that IP's main duty is to route the packets from source to destination. You can see it here. The header data is present. There are two parts in your IPv4 header. The first one is the header part, and the second one is your data portion. The header portion, if you see, I mentioned the size as 20 to 60 bytes. This is not a fixed sized header. The minimum size of the header is 20 bytes. Minimum size is 20 bytes. And the maximum size is 60 bytes. So it must be at least 20, that is 160 bits. And it can be a maximum of 60 bytes. Okay. Now let us see what are the fields that are present here. The first field is your version field, followed by the header length field, and then comes the differentiated services field, which is of 8 bits in length, and next comes the total length, which is 16 bits. We also have the identification. These are the three flags. These are the flags field, which consists of three 1-bit flags. So this is used for future purposes. It's not at all used right now. And then we have the fragmentation offset, which is of 13 bits in length. Then we have the time to leave field, which is 8 bits in length. Protocol field, which is once again 8 bits in length. And then the header checksum, which is of 16 bits in length, which is followed up by the source IP address, destination IP address. Both these addresses, if you see, they are 32 bits in length. This is 32 bits. And this is also 32 bits. After this header, you have options. Once again, as the name itself suggests you, they are optional. They are not mandatory that you need not place them into a IP header. You can add them if you need, and you can you need not add them if you don't want to. The 20 bytes which I spoke. So if you add 1, 2, 3, 4, and 5. So what is the length here? 32 bits. 5 into 32 gives me 160. So your minimum 20 byte header consists of all these fields which are marked in white. Options field and then followed by the data field. They are optional. You might have data or you might not have data. You might have options or you might not have options. Okay. We will discuss each one of these fields in detail, what work it does. So IPv4 defines the format of a packet in which the data coming from the upper layer or other protocols are encapsulated. Packets used by the IP are called as datagrams. So in IP, because it is a connectionless service, usually IP packets are also called as datagrams. What is this encapsulation? I will show you with an example. So a datagram is a variable length packet consisting of two parts. One of it is the header part and the other one is your payload or your data. The header is anything between 20 to 60 bytes in length and contains information essential to routing and delivery. All this is the essential information which is required by routers to analyze the packet and decide how this packet should be routed to towards the destination. Okay. Now, as I'm speaking about the encapsulation process, let me show you usually just how it actually does. Imagine that this is the message that you just typed. Your application layer sends this message to the transport layer. At the transport layer, let us consider this as the application layer's protocol data unit. I'm calling them as APDU, application layer's protocol data unit. This you will have the appropriate header of either TCP or UDP based on the application you are using. If you are using a connection oriented service, you have to use TCP header. If you want to use a connectionless service, you go for a UDP header. Now this message or this we call it as a segment. This segment is now forwarded to the network layer. Network layer, after accepting this, now this I will consider as the transport layer's protocol data unit. So I call it as TPDU. This TPDU, IP will accept it and it will now add this particular header to it. This is the IP header that we are just discussing about. So this, after adding this and after encapsulation, we call it as a packet. We call it as a packet. This packet is then forwarded or handed over to the data link layer, where we add a frame header and a trailer. Then we start calling it as a frame. We add a frame header to it. Then the packet, whichever is here, is encapsulated here and followed by the trailer, which is used for error control by the data link layer. So this is how the encapsulation process happens in the IP across the network, how the packet is actually being delivered to the destination. So this header is the part which I am showing here. So this is the header which is actually added to the transport layer's forwarded data or the segment we encapsulate it. So let us start discussing about each one of these fields in detail. The first field is your version number, which is of 4 bits in length. And as I told you, there are 2 versions of IP. One of it is IPv4 and the other one is IPv6. So for IPv4, you have the version as 4. These 4 bits specify the IP protocol version of the datagram. Now, because it's IPv4, this value will contain 4. By looking at the version number, the router can determine how to interpret the remainder of the IP datagram. So different versions of IP use different datagram formats. Either you have 4 or 6, that's all. Okay, we don't have any other versions. Now, what about the header length? The header length or the H length field defines the total length of the datagram header in 4-byte words. Now you have 4 bits, right? You have 4 bits. So the maximum value that I can have for 4 bits is 15, right? So the maximum value of the header is 60 bytes. So if I'm using a full sized header, this is the value. My header length value will be 15. Now what is it for the minimum value? The value of the header length field should be at least 5. Can you tell me why 5? Because 5 into 4 gives me 20 bytes. If the header is less than 20 bytes, then I have to assume that there is some error while transmitting and this packet is to be left out. You should not consider that packet, discard it. Now, the minimum length, the minimum value of this field is 5, because unless until it is 5, you don't get the 20 byte size. The maximum length is 15, which allows you the maximum header length is 60 bytes. This field is required as the IPv4 header is of variable length and the receiver needs to know where the header ends and the data starts. Unless until I tell you what is the header length, how would the receiver know that I added some options and the header length is so many bytes? If it is fixed size, I need not mention, but it is not fixed size. It is a variable sized. So when it is variable size, it is my duty to tell the receiver that, hey guys, the header length is so much. From this point onwards, you can count the data. That is the reason I'm having a header length field here. Next comes a service type field. So there is slight confusion when you check out the old books. You have this field name as type of service field, but in almost all the recent books, you have the differentiated services field. The actual version now contains differentiated services only because it is being redefined by IETF. The type of field, both of them are 8 bits in length. If you are using the service type field, the first 3 bits are called as the precedence bits and the remaining 4 bits DTRC. D tells you what is the delay, T tells you what is the throughput, R tells you regarding the reliability, C tells you the cost, and the last bit is reserved and it is not used. If you come to the differentiated services part, the first 6 bits are called as differentiated services code point bits, and the last 2 bits we call them as ECN bits, which is used for explicit congestion notification. If at all a router or a particular node is facing congestion, in order to convey that information to the others, we use those 2 bits. So we call it as service type, and this particular field is called as differentiated services. We have 8 bits. To talk about it a little bit more, the differentiated services field in the IPv4 header is used to classify the IP packets so that routers can make the quality of service decisions about what path the packet should traverse across the network. So this is actually helping the router to give or to provide the quality of service as per the requirement of that particular packet. So this is where we specify to that. We also call it as PHB, per hop behavior. So this DSCP is defined in the two RFCs of 2474 and 2475. The first 6 bits are used to mark the packet with its service class. It might be assured forwarding, and the last 2 bits are used to carry the explicit congestion notification information, such as whether the packet has experienced congestion or not. Now you can have a quick look with this particular example. As I told you that these are the first 6 bits. There are 2 classes that are defined. One of it is called as assured forwarding, and the other one is called as expedited forwarding. Both of them have its own PHBs. So a router or end host assigns one of the 64 possible forwarding behaviors. Where do you get the 64 from? 6 bits. 2 power 6 is 64 possible forwarding behaviors known as the per hop behaviors, PHBs. A PHB provides a particular service level. So each PHB defines one particular service level. It might be bandwidth, queuing, or dropping decisions, whatever it might be. The policy is based according to the network, in accordance with the network policy. So this is the purpose of this particular field, to provide information to the routers regarding the quality of service requirement of the packet. So when you are sending the packet, what is its quality of service requirement? In order to specify that, you do this with this particular field. So it is of 8 bits in length. It is of 8 bits in length. The first 6 bits are called as DSCP bits, differentiated services code point bits, and the remaining 2 bits are your explicit congestion notification. If you want to inform a particular node regarding the congestion that you are facing, then you need to add those bits there. You can use these 2 bits to signal the congestion that is happening. Now, next comes the total length field, which is of 16 bits in length. So the maximum you can have is 65,535 octets. It defines the total length, which includes the header and the data of the IP datagram. So this field allows the length of a datagram to be up to 65,535 octets. So this field helps the receiving device to know when the packet has completely arrived. So once you see the header length, it will know that what length is the header and from which point the data starts. And the total length will tell the receiver that where the actual packet heads. So what is the length of the data? The total length minus whichever value is placed in the header length into 4. So this gives me the length of the data or the payload of your IP packet. So the receiver can know that till it reaches there, this packet has ended, and it will remove that packet from the network and start analyzing it. The next 32 bits, which includes your identification of 16 bits, the 3 flags of, let us say this is 111, these 3 flags, and the remaining 13 bits are your fragmentation offset bits. This particular 32 bits are used for IP fragmentation. Now you can ask me, what is the fragmentation? Why do we need it? Now the packets are all not of the same size, isn't it? One might be a large packet, one might be a small packet. In some cases, there is a value called as MTU, maximum transmission unit, which is the maximum amount of data that you can send on the link at a single time. Not all the packets come below that particular size, isn't it? The packet might be huge. It might not fit into the MTU. So what you usually do is you fragment the packet into pieces, send these pieces onto the network, and at the receiver, let the receiver reassemble all these fragments into one packet and then deliver it to the transport layer. Basically, you are breaking the packet into smaller pieces, sending the pieces to the receiver, and at the receiver asking it to reassemble them properly and then forward it to the upper layer. But the problem here is, when you do that, how does the receiver know which part goes where? Which fragment, which is the first fragment, second fragment, third fragment? It doesn't know. To help in that purpose, we require all these bits. First, let me start with your identification bit, identification part. If an IP packet is fragmented during the transmission, all the fragments contain the same identification number to identify the original IP packet they belong to. Now, if you have one packet and they divide it into 10 pieces or 10 fragments, all the 10 fragments will have a common identification field, so that the receiver will know that these 10 fragments belong to the same IP packet. It will only determine that based on the identification field only. If they have a common identification field, it will accept or it will consider them as single packet. The next comes the 3 flags. The first flag is never used, or this first flag or the first bit is never used. And then we have 2 things, DF and MF. DF actually stands for don't fragment. MF stands for more fragments. If you are specifically telling a particular router not to fragment this packet, if it doesn't fit in the MTU, ignore it, send it back, but don't fragment it. In order to convey that information, you put a 1 here. If a packet contains DF as 1, the router cannot fragment it, or it is not supposed to fragment it. Okay. What about this more fragments? As I told you, if I break a small packet into 3 pieces, for the first one and second one, I have to tell the receiver that there is another one coming. Right. For those 2 packets or those for 2 fragments, I will say MF as 1, which means that I'm telling the receiver there are more fragments coming. This is not the last fragment. But for the last fragment, what I will do is I'll put MF as 0, so that the receiver knows that there are no more data left. This is the last fragment. And simply I'm conveying to the receiver there are more coming and which is the last one. That's all. So for that reason, these 2 flags are used. What about this fragmentation offset? This is very important, because when I divided the large packet into fragments, these 2 flags I can only convey that which is the last fragment, but I don't convey whether it is third one, fourth one, fifth one, or sixth one. This offset value will tell the receiver while reassembling the fragments which fragment goes in which place. This field tells the exact position of the fragment in the original IP packet. The fragment offset is measured in units of 8 octets. Okay, for the first one, it has an offset 0. So to understand this better, let me take a small example. Then we can have a clear understanding. Consider a datagram of 4000 bytes. Let me assume that I have a datagram of 4000 bytes in length, which has the 20 bytes of IP header and the 3980 bytes of IP payload. But unfortunately, the link MTU is only 1500 bytes. I cannot send more than that. Out of these 1500 bytes, you have to have the 20 bytes of header, isn't it? It's mandatory. So what you have to do, you have to break up your 3900 bytes of data into pieces. How many pieces can you make? You have to make 3 pieces. First one will have 1480, second one will have 1480, and the third one will have 1020. Altogether, put together, you get 3980. So you have to break them into 3 fragments. Each fragment has to be transmitted as an individual datagram. So each fragment will have its own IP header, isn't it? So for those 3 fragments, let us assume that the identification number is 111. So I now have one big packet which is of 4000 bytes, which includes the 20 bytes of header. This I have broken up into 3 pieces. So piece 1, piece 2, and piece 3. Let me call them as fragments. So how does these 3 values help the receiver to understand which fragments are this, whether it is the first fragment, second fragment, or third fragment? Because you have to keep in mind that IP is connectionless and it does not guarantee the in-order delivery of packets. So when you are sending a packet to the receiver, you cannot guarantee that these packets will be delivered in order. Second fragment might go first, third fragment might go first, first fragment might go later. It might happen. There is no guarantee there. So in that case, what you are going to do is, for the first fragment, because anyhow I'm dividing it, the do not fragment is 0. The more fragments is set to 1, and the first one is set to offset is 0. So for the first fragment, because we are starting with the byte number 0, it is always 0. So when the receiver receives this, it will know that, okay, because it is offset 0, this is the first fragment. What about the second and third one? For the second one, we have the same DF as 0. We are showing that MF as 1, which means I'm telling the receiver, here, there's something else coming. More fragments are coming. So wait for it. So for this, the offset is 185. Where did I get this 185 from? If you multiply 185 into 8, because the offset is calculated in 8 bits, you can see in units of 8 octets. In units of 8. Okay. So 185 into 8 gives me 44, 8 is 64, 8, 6, 1480. I'm saying that the first 1480 bytes are here. For the second part, You are starting from, again, you are sending 1480, but you are starting from 1480 onwards. So this is the second one. So how does the receiver know this is the second one? It sees offset as 0. It will put into the first position. It sees offset 185, puts it into the second position. And once the third fragment comes, but the receiver doesn't know that this is the last fragment yet. It reads this. It says MFF 0. It says MFS 0. So once it says MFS 0, automatically you have to understand that this is the last fragment and it will add towards here. The last one is 1020 bytes. Okay, sorry, this offset is not 0. I made a mistake. The offset is not 0 there. Okay, so what I am saying is, so for 185 plus 185, it should be 370. It should be 370. My mistake. So the data sent is 1020 bytes. So 3980 minus 1480 minus 1480, which gives me 1020, which is sent in the third fragment. So in this way, the receiver, by using these 32 bits, can understand how to reassemble a fragment, because the receiver doesn't have any prior information. How many fragments I made, where, how did I do? It doesn't have any information. Only from that header only it can understand and reassemble these fragments together at the receiver side. So next field is your time to live field. This is nothing but you need to ensure that the packet does not live for a long lifetime throughout the network. I do not want a packet to live forever. So once its lifetime expires, I need that packet to be discarded. For that purpose, I have a field called as time to live field. It is included to ensure that datagrams do not circulate forever in the network. So once the packet is created, I will set a particular value in the time to live field. This is 8 bits in length. So of this 8 bits in length, the maximum value I can have is 255. Let me assume it is 255 seconds. So for every second, it gets decremented. So if it does not reach the particular destination before your timer reaches 0, then that particular datagram must be dropped or discarded. If it goes to the destination before TTL field is valid, then it's fine. But for whatever purpose, if a packet is keep on traversing the network, wasting all the routers, CPU cycles and buffer space, why do you want to keep it? So this particular field is clearly designed in such a way that, or clearly kept in such a way that, we do not want a packet to traverse forever in the network. A packet must have a fixed finite lifetime. For that, we have the TTL field. For every hop, you actually decrement it, and for once it reaches 0, you simply discard the packet. Next comes the protocol field. This field is used only when an IP datagram reaches its final destination. As I told you, the receiver's network layer, what it has to do, it has to accept the packet, analyze it, check for any errors if the checksum is used, and then has to forward it to the transport layer. In transport layer, there are two protocols. One of it is TCP and the other one is UDP. So to which transport layer must the received packet should be delivered? That is a issue. So for that purpose, we included a protocol field which will tell the receiving network layer to which protocol you should hand over it to. A value of 6 indicates that the data portion is passed to TCP, and a value of 17 indicates the data is passed to UDP. So this protocol field is used to indicate the specific transport layer protocol to which the data portion of this IP datagram should be passed. And finally, we have the header checksum. So the header checksum aids a router in detecting bit errors in a received IP datagram. We have a 16-bit checksum here. This is the same way that we calculated earlier in my videos. So it is computed by treating each 2 bytes. 2 bytes is 16 in the header as a number, and summing these numbers using the ones complement arithmetic. This is nothing but the internet checksum method, which we did a few examples on in my earlier videos. So it's a 16-bit checksum that is used for IP header. Okay. Next comes the two addresses, your source address and destination address. Both of them are 32 bits in length, which identifies who created this packet, and your destination address identifies to which host this packet is destined to. Finally, we get the options part. As I told you, the options name itself suggests they are optional. You might add them or you might not add them. You can ask me, sir, if you don't need to add them, why are you telling us all this? Because The fixed header value will give you information to route it to for a router to take a decision, which is the source part, which is the address, which is the destination address, all those things. These options do provide a little bit more information, which would aid for better analysis of the packet. So these options may contain values for options such as security, record route, timestamp, etc., which are primarily used for network testing and debugging. Network managers, administrators use these particular options in an IP header to find out or any problems with the issue or to debug any issues with the network. Though options are not a required part of the IP header, option processing is required of the IP software. There are two types, 1-byte options and multi-byte options are present. Finally, you have the payload or data, which is the main reason for creating a datagram. The data field of the IP datagram contains the segment whichever it is passed on from the transport layer. And of course, it might not be a transport layer. Sometimes you might have an ICMP packet, which is encapsulated within an IP packet also. If you are sending an error message using ICMP message is also included into your IP packet only. It can be also encapsulated. These are the IPv4 options, as I told you. These are some of the common options that we have. The first option is the security one, which specifies what is the security level that you are providing to this datagram. Next comes your strict source routing. The strict source routing tells you that what is the path the source has selected for this datagram to traverse. So this gives you a sequence of IP addresses. The datagram is expected to follow that particular route only. The datagram is not supposed to go to any other router else. That is called a strict source routing. If it is implemented, the datagram has to follow the addresses or the routers selected by the source only. Sometimes if not that strict way of implementing it is your loose source routing. It also requires the packet to traverse the list of the routers specified by the source, but it can also traverse the other routers also. In strict source routing, it is not an option. Only the router specified by the source, the packet is supposed to go. In loose source routing, in addition to the routers that are mentioned by the source, your packet can traverse other routers also. It is permitted. For record route option, each router along the path is to add its IP address to the options field. So whenever a packet reaches a router and the packet analyzes this, the router analyzes this packet and forwards it to the next outgoing link, the router will add its IP address to that particular options part. A maximum of 9 routers can add their addresses when you add this particular record route option. This is also once again used to track down how your routing algorithm is being used. Are there any issues with it? All those kind of things. For debugging, you can use this. And the last option is your timestamp option, which just like the record route option, not only just adds the 32-bit address, but also the timestamp at which the router has analyzed this packet. The router, when it analyzes, it will actually add the timestamp to it also. And as I told you, this particular option is primarily used for taking measurements of the routers to measure the delay, all those kind of things. We add these options. Let me just summarize. IPv4 options are not mandatory. You can add them, or you might not add them into an IPv4 header, but the header must be anything between 20 bytes to 60 bytes. The 20 bytes are mandatory, and you can have at the maximum of 40 bytes of options at a point. So the total length of the header is 60 bytes. So that's it for regarding the IPv4 header. And as I told you, regarding the IPv4 addresses and submitting, I'll create another video. So until then, take care. Hope you enjoyed it. So do share and subscribe. Thank you very much.